So today we're going to take a look at how we measure solutions, and the terms that we acquire in this section are going to be used pretty much throughout the rest of the year. And since we're dealing with solutions, we should probably discuss how they're made, and that means that we need a couple of terms. And we want to be able to differentiate between the terms solute and solvent. And to keep them straight, I'm going to show you a technique that was taught to me about 30 years ago, and I still remember it. And to kind of get us into the mood, I'd like you to watch this clip from one of my favorite Disney movies of all time. So this clip's about 9 or so minutes long. Feel free to fast forward to the end if you don't want to watch the whole thing, because I will bring you back to the reason why I'm showing it to you, which is going to seem a little off topic at first, but I promise it's relevant. All right, so make some popcorn and check this out. So if you haven't figured out yet why I showed you that scene, that whole vignette from this particular movie, it is because of this scene, and I've got a screenshot that I want to show you. It looks like this. You can remember this scene of all these, for lack of a better word, possessed or animated brooms standing on this flight of stairs getting ready to do the task they were assigned. If you can hold on to that, that'll make this a bit easier. So let me get a better picture here. And this is how we're going to keep in mind the difference between solute and solvent. Here was what I was taught about 30 years ago. So I'd like you to imagine, if you will, that you have a cup of hot coffee in front of you that, it's breakfast, it's morning, you got to get your coffee going. And so here is a cup of hot coffee, and it's got steam coming out of it and all that stuff. And you're one of these people that likes a bunch of sugar in your coffee, and you don't like to just pour it in. You like to use a sugar cube. And so you've got your sugar cubes, and they're like this. So I'm going to apologize for the crudity of this drawing. And let's say that you like about 20 sugar cubes in your coffee. It's just the way you roll, I guess. And because you're an apprentice sorcerer, you've been practicing, you don't want to put your sugar cubes in your coffee by yourself, so you're going to let them do it. And so here's what you have. You've got your sugar cubes, and you've cast a spell upon them, and they, rather than you putting them in, are putting themselves into your coffee. And you've built a nice little flight of stairs that they are happily walking up. And here is the trick. As they get to the top, and right before they dive in, they salute. So if you can keep this in mind, you will always keep this straight. The solute salutes the solvent. If you can keep that in mind, you will always remember that is the solute that goes into the solvent. So let's take a look at how this works. It's this term concentration, and it is a general term for how strong a solution is. If you're making lemonade and you don't use enough of the lemonade mix in your water, it's not going to taste very strong. It's not very concentrated. If you use way too much, it's going to taste awful. It's going to be way too strong. It's going to be way too concentrated. So this term concentration is a very loose term that says how much solute is in the solvent. And we're going to use two versions. The first one we're going to use is called molarity. It's going to be abbreviated with a capital M. Let me make sure that looks like a capital M. Now, you've seen this before. This this unit molarity before, even though you may claim you have never heard of it. Let me show you where you've seen it. Came from Lab 11D that we just did last week at the end of Chapter 11. And if you recall, I said that this is a 3 molar solution of hydrochloric acid and that it is very dangerous. This, capital M, is this. And what it means is number of moles of solute, what we are dissolving, per liter of solution. So what this means, this 3 molar hydrochloric acid, what this means is that we have 3 moles of hydrochloric acid in every 1 liter of solution. So let me show you how this works. We'll try a couple of calculations. And it's a really simple set of calculations. Let's do it in a shorthand here. Molarity is equal to moles over liters. And I'm going to ask you to do this in a couple different versions. And so a good way to do that is with what we call a devil's triangle. And the way a devil's triangle works is this. And you've probably seen one before. So let's make this a little smaller. If I was going to ask you to calculate molarity, you'd say that molarity is equal to moles over liters. If I was going to ask you to calculate volume in liters, you would say that liters is equal to moles over molarity. And finally, if I was going to ask you to calculate how many moles, you would say that moles is equal to molarity next to liters, which is, of course, multiplying. So let's try a real simple one. And we'll do an example of a problem you could expect me to ask you guys to try. Here's a good example. What's the molarity of 90 grams of HCl in 500 milliliters, otherwise known as 0.5 liters? So obviously it's asking for molarity, and that means it's moles over liters. So the first thing that we're going to want to do is find out how many moles of our solute, how many moles of HCl do we have? If we have 90 grams. Now, some of you guys round a little differently. I round chlorine all the way up to 36, and that makes the molar mass of HCl 37 grams, right? Because hydrogen's 1, chlorine 35.5. I rounded up to 36, so that's 37 in 1 mole. So make sure you have a calculator handy because we're going to need one quite a lot. Let me turn on my fancy one. Bingo, and what we're going to say is 90 divided by 36. This tells us how many moles of solute we have. 2.5. Now, what we want to do is find out what the concentration is. So to do that, we're going to plug that into the equation for molarity, which is this guy. So what's our molarity? We've got 2.5 moles of HCl. And how many liters of solvent do we have? 500 mils, otherwise known as 0.5 liters. I don't think you need a calculator for that one, but if you do, here's what it looks like. We're going to take our 2.5 and we're going to divide that by 0.5 liters, the same as multiplying by 2, and that means that we have a concentration of hydrochloric acid that is 5 molar, a little bit stronger than the 3 molar that we used in Lab 11D. Okay? Now I may ask you to find moles, I may ask you to find grams, I may ask you to find volume, but that's what this guy is for. All right? Let's do the other version of this, and this is one that we're going to use quite a lot in the second part of chapter 13, and this is called molality. And it's really similar, but we're going to abbreviate it with a lowercase m. And this is number of moles of solute for every kilogram of solvent. So it's really similar. And because it's so similar, we can plop this into a triangle just like we did with molarity. So if molality, lowercase m, is equal to moles over kilograms, let's bonk this into a triangle like we're used to. And what we're going to say is, okay, we know molality is equal to moles over kilograms. That means that molality is equal to moles over kilograms, and we know that one. It also means that if we are trying to find how many kilograms of solvent we have, it's equal to moles over molality. And finally, if we wanted to find how many moles of solute we had, it's equal to molality times kilograms. I want to make that smaller. Just so it doesn't take up so much space, you know what I mean? And it's not erasing, but that's okay. Molality is equal to moles times kilograms. Let's do a real quick one here, and then I'll shut up and let you guys try this, okay? So let's get an example of a question you might expect to see. All right, now this one's actually going backwards, and now that I am doing this, I realize I've put a little typo up here. So let's erase this, because if we're trying to find moles, it would be equal to molality times kilograms. Good thing I caught that. See, even the pros make mistakes, ladies and gentlemen. So this question is asking how many moles, if we know our mass of solvent and how many moles per kilogram we have, otherwise known as molality. So it's asking moles, and we know, according to our triangle, despite what I said earlier, I beg your pardon, that moles is equal to molality times kilograms, right? Molality is right here. Moles, excuse me, is right here. Molality, and it's next to kilograms, all right? So forget what I said earlier. Speaking about not having your coffee, right? So this one is asking how many moles? Well, we know we have a 4, this is supposed to be yellow highlighter, and my OneNote is really slow, 4 molal solution. So we're going to put that right here, 4 molal solution, and we have 0.3 kilograms. So let's bust out our calculator. I'll use my fancy one, and we'll say, turn it on first, that we have a 4 molal solution times 0.3 kilograms, and this is a 1.2. I've also caught OneNote on a morning when it hasn't had its coffee yet. So trying to erase what I just did here. Let me pause. There we go. So this is a 1.2 moles of solute. Now, if I was going to say that this is our solute, C5H10O5, I could seriously ask you to tell me how many grams we have, but I'm not going to do that today, all right? What I would like you to do is to practice a couple of each of these. Honors chemistry, if you're watching this, we're going to do it all in one big shot. General chemistry, if you're watching this, we'll break this up into a couple of different sections, okay? So remember to keep these two triangles close by. Molality, capital M, is equal to moles over liters, and molality, lowercase m, is equal to moles over kilograms. So when you're flipping these around, we know that molality is equal to moles over liters, moles is equal to molarity times liters, and liters is equal to moles over molarity. If we're doing the same thing with molality, molality is equal to moles over kilograms. Kilograms is equal to moles over molality. And the last one, which I screwed up earlier, moles is equal to molality times kilograms. Okay, good luck. See you guys on the next one.